Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at what are called separable differential equations. Differential equations. Well, here's how it looks. A separable differential equation looks like this. It looks like dy dt is equal to some function g of t times divided by some function f of y. In other words, we can take it into just two separate pieces. And here's how we solve it. We multiply both sides by f of y. So we get f of y dy dt is equal to g of t. And then, if you will, then we take the integral of both sides with respect to t. So what happens then essentially is when we do this, we're going to have the t's, you could think of them as canceling out or just taking the integral with both sides to t. Whatever it is fine. So, but what we're going to do now is we're going to think of it this way, f of y dy. We're going to take that integral, and we're going to take the integral of the other side, which is g of t dt. Now, when we do this, what do we get? On the left-hand side, it's going to be some function of y. And on the right-hand side, we're going to have some function, capital G of t. And at this point, then the problem is solved. All you have to do now is just solve for y. Solve for y. So let's try one and see how this works. So let's try it. We're going to solve the problem of dy dt is equal to t over y. This is one of a more simple differential equations, but I think this should work just right. So we're going to multiply both sides by y. So I have y dy dt. I'll leave a little space in. No, I'll just do it this way. Equals t. Then we're going to take the integral of both sides with respect to t. Well, that just leaves me with a dy, integral of y dy equals the integral of t dt. And then we're going to take it, let's remember our limits of integration from some y of 0 to y of t. And so from 0 to t, and I want to notice one thing is we have a y in the denominator, so that means our initial condition cannot be 0 at 0. It could be 1 at 0, it just can't be 0. All right, so now that we've made that acknowledgement, we can continue. Well, this just becomes 1/2 y squared, or we'll write it this way, 1/2 y of t squared minus 1/2 y of 0 squared equals 1/2 t squared. And now look at this. We are right here. So our last step is to solve for y. I'm going to multiply both sides by 2. So y of t squared is equal to, minus a y of 0 squared is equal to a t squared. Let's add our initial condition. Y of t squared is equal to y of 0 squared plus t squared. And this is an implicit equation, and so it has two parts. We'll just take the positive part, just for illustration. Y of t is the square root of y of 0 squared plus t squared. And that is the solution using the property of separable differential equations. Now, I don't want to leave this quite yet because I think this seems a little oversimplified, and we're going to try another problem that's not so obvious. We're going to solve y prime minus a, or how about plus ay. Is that what we want? No, I think it'd be easier if we write minus. Minus a y equals q, where a and q are constants. Okay, if they're not constants, we would be using an integrating factor, but let's just look at this one unique case. So I'm going to start doing a little bit of a rearranging, and just so we can start trying to find, remember the pattern we're looking for is some dy dt has to be equal to some function g of t divided by some function of y. Okay, so we have to figure out how to rearrange this first order linear differential equation with constant coefficients into this form. All right, well obviously we need the y prime by itself. So here's y prime equals ay plus q. Well, on the left hand side, that's dy dt. Now on the right hand side, what you have to think of everything in multiplication. So the only way I can think to separate this into a function of t and y is let's factor an a. This would be a times y plus q over a. Now, this doesn't quite look like our g of t divided by f of y, but division and multiplication are kissing cousins, and so this shouldn't make a difference. So here we go. Let's see if we can solve this problem. In other words, I'm going to divide both sides by y plus q over a. So then I have 1 over y plus q over a dy dt equals a. And now we can take the integral of both sides. So we'll do that. So, whoops, let me give myself some space here. So it's 1 over y plus q over a dy dt equals the integral from 0 to t. Remember, you could write y of 0, y of t, but it doesn't matter because this is only in t's on the right-hand side of a dt. And there we did it. So in this case, f of y was really 1 over y plus q over a, and the function of t was the constant a. All right, let's integrate this. The left-hand side, that is, if you made a u substitution, that's going to give you the natural log of y plus q over a. So I'm going to just write that answer. That's the natural log of the absolute value of y plus q over a. And this on the right-hand side is going to, oh, no, that's not right. Minus, let me clean that up. That just looks sloppy. Minus the natural log of y plus q, y of 0, goodness gracious. Y of 0 plus q over a equals a times t. Okay, let's see. Let's move this initial conditions to the right-hand side. So now I have the natural log of y plus q over a is equal to the natural log of y of 0 plus q over a plus at. Okay, so now what we're going to do is we're going to have to raise each side. That's the only way we can solve for y. So we're going to exponentiate both sides. So I'll write that in. So really we're going to take and raise each side now to the e. I'm going to write it like this. E to that side and e to this side. Well, the left-hand side, that works out really nicely for me. That gives me y plus q over a. And let's just make a note here that y plus q over a needs to be greater than or equal to 0 in order for that absolute value to not be there. So that's our caveat to this solution. Equals, now I have this is a problem. I have e to the natural log of y of 0 plus q over a plus at. Oh, how do I, wait a minute, there's a plus. Remember, plus is what happens when you multiply with an exponential. So I could write this as y plus q over a is equal to e raised to the natural log of y of 0 plus q over a times e to the at. Oh dear. Oh, look at that. Well, now this is y plus q over a equals, well, e to the natural log, that's going to bring all of this stuff down. Y of 0 plus q over a times e to the at. All right, well, let's multiply this out and see what we get. We get y plus q over a equals y of 0 plus q over a e to the at. Oh, there it is. And our last step is going, oops, nope, I made a mistake. This would be y of 0 times e to the at plus q over a e to the at. Now we can write our final solution as y equals y of 0 e to the at plus q, and actually let's factor that e to the at. This is y of 0 plus q over a e to the at minus q over a. And there it is. That worked. Now I have to admit that I think the author leaves this as kind of a last option in our textbook is because it does create this strange difficulty where you always have to make these qualifications about the natural log of the absolute value. So the technique works. It requires this hand waving that we did, but you'll see it from time to time quite often. I think we'll stop there for this video. I hope that helps. Thanks for watching.